What's up? I'm Vin, and today I want to show how to evaluate improper integrals that have discontinuous integrands. So these are the 4 examples we're going to go through. Here's some notes to help us out, and let's get started. Okay, for this first question here, let's take a look at a sketch, and then we're going to go through these steps. So we want to think about which value makes the integrand 1 over square root 4 minus x discontinuous. And in this case here, the problem is going to be at x equals 4. Because when we have x is equal to 4, we're going to have 4 minus 4, so we'll have a 0 in the denominator, which makes this whole expression undefined. And if we notice here, if we look at a sketch of this, if we want to find the area from 0 to 4, that's this space here, we're approaching a vertical asymptote. So what we're trying to find here is, does this area actually converge to some value, or does the area spill off to infinity? So when we set up our integral, we just have to be, when we set up our limit, we have to be very careful thinking about what we're actually going to replace. So if we introduce a new value, let's say b, we're going to take the limit as b approaches 4, but now notice we're on the left side of this vertical asymptote. We're approaching from the left, so we're going to take the limit as b approaches 4 from the left side. And now we have the integral from 0, and just make sure you replace the right limit. Remember, the value that makes this discontinuous is x equals 4, so that's the one we're replacing with the letter b. And now we could write the integrand as 4 minus x to the negative 1/2 power. It's better to write it like this so that when we take the antiderivative, we could just get right to it. Okay? So remember, when you're doing these questions, just be careful. Replacing the limits could be a little bit tricky, but you want to replace the limit where the discontinuity is. So now when we go forward from here, we have the limit as b approaches 4 from the left side. And now when we take the antiderivative, we have 4 minus x. So we're going to keep the base. We're going to use power rule. Negative 1/2 plus 1 is positive 1/2. And then we write the reciprocal, which is 2. But notice the inside, I could have done a u-substitution here, but the derivative of the inside is negative 1. So then we just divide this whole thing by negative 1. And now we have the limits going from 0 to b. So we're just going to complete the fundamental theorem of calculus here, and we'll be able to answer this question. So now we have the limit as b approaches 4 from the left side. And now 2 divided by negative 1 is just negative 2. And on the inside here, we're just going to plug in the limits. We have 4 minus b to the 1/2 power. Minus, and we're going to have 4 minus 0 to the 1/2 power. All right, and if we want to put brackets around this whole thing, we can, just to show what we're actually plugging in. But now this limit is something we could evaluate by direct substitution. So now we have negative 2, and inside here, inside these parentheses, we have 4 minus b is approaching 4 from the left. So we're going to have 4 minus 4 to the 1/2 power, which is really just the square root of 0. So this part cancels out. And then we've got minus 4 minus 0 is just 4 to the 1/2 power. So if we work this out, now we have negative 2 on the outside, and then we have in the parentheses here, we have minus, and then 4 to the 1/2 power is just 2. So we get negative 2 times negative 2 is equal to positive 4. Okay, for this next question here, we want to find the area from 0 to 1 under this curve. And if we look at a rough sketch of this function, we're trying to find this area from 0 to 1. And once again, we have a vertical asymptote, and we want to see, does this curve get to the vertical asymptote fast enough that this area converges, or will it just spill out to infinity? So if we work this out here, once again, the key first step is identifying which value of x makes the integrand discontinuous. And if we were to use 1 or negative 1, we would have a problem with this expression. But notice the interval is just going from 0 to 1, so that's the value that we're going to go with. X equals 1 is a problem, and that's what we need to replace. So when we set up our limit, now we have the limit as b approaches 1, and once again, we're looking at this graph here. We're on the left side of 1 because we're on the interval from 0 to 1. So we're getting closer to 1 from the left side. And now when we set up our integral, we have the integral from 0 to b because we're replacing the value that makes the integrand discontinuous. And now we just write the rest. We have 4x over square root of 1 minus x to the 4th dx. But now for this step, I recommend doing the antiderivative on the side. And if we set up a u-substitution here, I'm going to let u equal x to the second power. Because then we're going to have u squared is equal to x to the fourth power. And I'll also have du is equal to 2x dx. So if we look here, the goal is to take the antiderivative of 4x over radical 1 minus x to the fourth power, here like this. And if we look at this, well, we have to replace the numerator portion 4x dx. So there's a few different ways we could do this. One way is to just double the du term. We have 2 times du. That would equal 4x dx. So then here, what we have is 4x dx gets replaced with 2 times du. And on bottom, now we have radical 1 minus x to the fourth power is u squared. But we should recognize here du over radical 1 minus u squared is the integral for sine inverse or arc sine. So we would have 2 times sine inverse of u and then plus c. So if we write this in terms of just x, we have 2 times sine inverse of x squared and then plus c. But remember, when we're doing an antiderivative for a definite integral, we don't need that plus c. But because we wrote it without limits here, we should write the plus c. So for the next part, we have the limit as b approaches 1 from the left side, and the antiderivative without the plus c is 2 sine inverse of x squared. And our limits are going from 0 to b. And now from here, to work this out, now we just use the fundamental theorem of calculus. So we're just going to plug in the limits and subtract. We've got 2 times sine inverse of b squared minus 2 times sine inverse of 0 squared. Now sine inverse of 0 is 0. So this part just cancels out. So then when we want to evaluate this, we just plug in. We have 2 times sine inverse of 1 squared. And it doesn't matter if we're approaching 1 from the left or the right. We're just going to plug in 1. We're evaluating this limit by direct substitution. And now we have 2 times sine inverse of 1. And sine inverse of 1 is equal to pi over 2, because sine of pi over 2 is equal to 1. And now these values cancel here, and this is just equal to pi. All right, for this third question here, let's look at a sketch of x natural log x. And we're trying to find the area between 0 and 1. And this question's different because now we're not dealing with the vertical asymptote. We're dealing with the hole in the graph. So for this question, we have to go with a different approach. And notice that this time around, if we think about which value of x makes our integrand discontinuous, x equals 0 is our problem here because natural log is only defined for positive values of x. So 0 is not going to work for natural log x. So when we replace this with our limit here, we're going to do the limit as b approaches 0. But now if we think about it carefully, if we're on the interval from 0 to 1, and we could also use the graph to help us here, we're approaching 0 from the right side. So that's just something we have to be very careful with when we set up this limit, that we make sure we use the correct side. So we're approaching 0 from the right, and now we have the integral from b up to 1. Remember, once again, we're replacing 0, so that's where the variable is going to go. And we have x natural log x dx. Now, once again, I highly recommend that you do these antiderivatives on the side if there's more than one step to do. Like, this is a somewhat complicated integral, so we should do the work on the side. And here, we're going to use integration by parts. We're going to have u equals natural log x. So then du is going to equal 1 over x dx. And then dv, we're going to define as x dx. So then v would equal the antiderivative 1/2 x squared. And we're going to save the plus c for the very end. So this integral, if we work this out, is equal to u times v. So we're going to have 1/2 x squared natural log x, and now minus the integral of, and we have v times du. So we're going to have minus 1/2, and we've got x squared times 1 over x dx. So if we work this out a little bit more, this is 1/2 x squared natural log x minus 1/2, and now x squared times 1 over x is just x dx. So then when we work this out to the final step here, we have 1/2 x squared natural log x. The antiderivative of x is x squared over 2. So this is going to give us minus 1/4 x squared. And because we started with an indefinite integral on this side, we'll just throw in our plus c so that this side is technically correct. But now when we use that information over here, all we're going to do is we're going to rewrite our limit as b approaches 0 from the right. And now the antiderivative could go here. We have 1/2 x squared natural log x, and we've got minus 1/4 x squared. And our limits are going from b up to 1. Remember, we don't need the plus c here because we're dealing with a definite integral for this expression over here. So now we make the substitution. We have the limit as b approaches 0 from the right side. And when we plug in the upper limit 1, we're going to have 1/2 times 1 squared, natural log of 1, which is 0, so this term cancels out, and then minus 1/4 times 1 squared. And now we have minus, and we're going to plug in the b term here. So we have 1/2 b squared, natural log of b, and then minus 1/4 times b squared. So this is kind of like, yeah, this expression is, there's a lot going on here. But now if we work this out a little bit, we're going to see what we have left. We have the limit as b approaches 0 from the right. And we've got negative 1/4 times 1 squared is just negative 1/4. Just make that a little bit neater. So we have minus 1/4. And then we're going to have minus 1/2 b squared, natural log of b. And then we have minus 1/4 b squared, which is going to change to plus 1/4 b squared. Now, this would be nice if we could just evaluate this limit by direct substitution. However, this middle term here is going to be the problem, because as b approaches 0 from the right, we're going to have 0 squared times negative infinity, because natural log of 0 from the right side, natural log goes towards negative infinity as we approach 0 from the right side. So this middle piece here is a complicated piece that we're going to have to actually look at on the side here, because 0 times infinity or negative infinity is an indeterminate form. So just on the side here, we're going to evaluate this limit. We're going to have the limit as b approaches 0 from the right, and the coefficient negative 1/2 I'm not going to include. I'm only going to look at this, b squared times natural log of b, which once again is 0 times negative infinity, which is an indeterminate form. So what we're going to do first is rewrite this as a fraction so that we could use L'Hopital's rule. So this is natural log of b divided by b to the negative second. So we're just sending this down to the denominator. So now when we use L'Hopital's rule, we're going to have the limit as b approaches 0 from the right, and we're going to have 1 over b in the numerator, and we're going to have negative 2 times b to the negative third power in the denominator. And if we simplify this a little bit, now this is the limit as b approaches 0 from the right, and we're going to have negative 1/2, I'll just write on the side, this 1 over negative 2 piece. And then 1 over b I could write as b to the negative 1, and then b to the negative third I could send back up as b to the third power. And if we work this out a little bit more algebraically, we have the limit as b approaches 0 from the right, and we've got negative 1/2 times b squared. So now we could plug in 0, and 0 squared times negative 1/2 is just 0. So this term here actually goes to 0, which means the entire limit is going to be negative 1/4 minus 0, because once again, this term converges to 0, and then plus 1/4 times 0 squared is 0. So the area converges to negative 1/4, or we should say the signed area converges, because remember, this part of the graph was under the x-axis, so it makes sense that our answer comes out negative here. Okay, for this last question, we're going to have a case where the point of discontinuity is between the limits of integration. Because if we look at this function here in a sketch, at x equals 2, we're going to have a denominator of 0, which is also going to make a vertical asymptote in the graph. So what we're trying to find is the integral from 0 to 5. So we want to find this region here from 0 to 2 and see if this area converges. And then we also have to have this area from 2 to 5 converge as well. If one of these regions diverges, then we would say that the entire integral from 0 to 5 diverges. So the idea behind this is we want to break this up into two separate integrals. The integral from 0 to 2 of x over x minus 2, and then we have the integral from 2 to 5 of x over x minus 2. So once again, we have to check these one by one, and we need both of these integrals to converge for this entire integral to converge. So if we start with the first one, the integral from 0 to 2 of x over x minus 2. Looking at this specific integral here, notice the problem for us is that x equals 2. And if we look here for the interval from 0 to 2, we're approaching 2 from the left side. So when we write our limit in the next step here, we're going to have the limit as b approaches 2, but for this particular integral, we're on the left side of 2. So we're approaching 2 from the left, and we have the integral from 0 to b, and we have x over, just make that neater, x over x minus 2 dx. Okay, so for this part, the antiderivative step, we're going to just do that work on the side because this u-substitution is a little bit tricky. There's a lot to write, and we don't want to have to keep rewriting this limit notation. So we would actually let u equal x minus 2, and that would tell us du is equal to dx. But there's another step we have to look at here. We have to come up with an expression involving u to replace x. And if we solve for x, would equal u plus 2. So we're just solving our original definition of u for x. So when we plug everything in, now we're going to have x is equal to u plus 2. X minus 2 on bottom is equal to u, and dx is just equal to du. And what this allows us to do is now we could divide each term by u. We have u over u is equal to 1 plus 2 over u. Here like this, and then du. We couldn't do that in the beginning because the denominator was in multiple pieces, not the numerator, so this substitution was definitely necessary. So now the antiderivative of 1 is equal to u, and the antiderivative of 2 over u is 2 times natural log absolute value of u, and we have our plus c at the end. So now from this step, we're just going to plug back in for u. U is equal to x minus 2. So we've got x minus 2 plus natural log absolute value x minus 2. And we'll just write our plus c at the end. But when we use this for our definite integral, we're not going to need that plus c. So for the next line here, what we have is this is now the limit as b approaches 2 from the left side, and the antiderivative in terms of x, we have x minus 2 plus natural log absolute value x minus 2. And now we just write our limits. This is going from 0 to b. So from this step here, now we just have to make a substitution and then evaluate the resulting limit. So we're going to have the limit as b approaches 2 from the left. We complete the fundamental theorem of calculus, which I'll write in two separate colors here because it's just a lot to plug in. So we have first b minus 2 plus natural log absolute value b minus 2. And now we have minus, and we're going to plug in the lower limit. We're going to have 0 minus 2 plus natural log, and let's just separate this here so this doesn't overlap. So we have natural log absolute value, and we have 0 minus 2, which is absolute value of negative 2. And then we close out this whole expression. So now we just have to go through this piece by piece. We're taking the limit as b approaches 2 from the left here. Well, if you think about where this is headed, we're going to go term by term. If I were to replace b with 2, the first term is just going to go to 0. But this second term here is the one we have to be most careful with. As b approaches 2 from the left side, this is going to work out to a small negative number. Okay, so we need to really think about first, like just a graph of natural log of x, just to help us understand that limit. Okay, because if you think about what happens to b minus 2, well, b minus 2 approaches 0 as b approaches 2. So what we're looking at here is, and the absolute value keeps this positive the whole time, so we're not going to have to worry about negative numbers. But what happens as we approach 0 from the positive side, or we approach 0 on the right side of 0, we're going from right to left here, the entire expression goes to negative infinity. So we're going to have 0 And this term here is going to tend towards negative infinity. So this first term goes to 0, the second term goes to negative infinity, and now we have minus, and in the parentheses we have 0 minus 2 plus natural log of 2. But if you look at this entire expression here, the entire expression is just heading towards negative infinity. So if we think about what we just found, we were looking at the interval from 0 to 2. This tells us that this area in this section diverges towards negative infinity. So what we can say is that the original integral, which we'll just drag with us down here, so this original integral, we could just go ahead and say that the entire thing diverges. If we actually did come up with an actual value here, let's say this converged to something like -3, then we would have to also investigate this integral as well from 2 to 5 and see if it converges, and then just add the two values. But because one of them diverged, we could say that the entire integral diverges. Okay, well, this is going to conclude this video on evaluating improper integrals with discontinuous integrands. If you found this video to be helpful, please like and subscribe. It helps me grow the channel. And if you got any requests, just leave the topics you want me to cover in the comment section below. And thanks for watching.